Let us continue with the pile testing. So, by this I think you could understand the three concepts. Concept 1, foundation by means of simple spread footing for the Kent ledge itself, and basically piled foundation where the ground condition does not permit load distribution around the test pile. The primary concern is we should not put undue load to the pile soil interface which is being tested. So, that is why we have to space it larger enough, so that the pressure from the support pile, the Kent ledge support pile does not affect or influence the results of the test pile itself. That is one concern. The second concern, when you are doing a measurement of a displacement of the pile being tested, you need to have a firm ground or a datum line by which you will be able to measure the settlement. For example, in this case, if a ground condition is good and also you have accessible ground. So, you just put the datum line which is not going to change over a period of time during the testing. So, there is a easy way of putting a dial gauge with respect to the ground and then measure the movement of the pile. Now, if you go to the offshore condition, what happens is you have no firm condition or firm ground, you have to use only the pile which is supporting the Kent ledge, but at the time of testing it is not loaded anymore. So, you can use that as a reference and use a beam or some welded connection, so that you can use the dial gauge. So, what we need is the firm place where it is not moving during the testing. So, that is one of the second concern. And then when you are doing the testing, in any case it is not influencing the soil pile interface or the capacity of the test pile which is being done just now. So, that is one of the idea. So, you need to keep it far away, 3 to 4 diameters. So, your Kent ledge anyway will require a larger space to stack up the weights and things like this. Very rarely, even coastal areas, we do this because it is very expensive. One of the tests could take months to set up and do it and bring back. So, a typical Kent ledge test which is just on land. So, you can see here, even in this particular case, it was done in one location in Kakinada, where last year, the year before, you can see piles were driven. So, this ground condition was so bad that even you can't spread the load which coming from so much of sandbags. So, we need to have piles going down to a firm ground, because the total top 15 meter of soil is a clay, soft clay, and if you try to put some spread footing, it will definitely sink under this kind of support reaction load during stacking, and then you can't retrieve. Then every time when you just load and unload, the foundation becomes no use. So, that is the picture that you are seeing. The pile is being tested, which is at the middle, and basically the pile will be provided with a pile cap, steel plate, and these are the jacks which are just placed between the Kent ledge and the pile head, just to stack up, and the dial gauge you can see here is placed at this place, and if this is the reference to the pile head itself, and this is the datum line which is not moving. So, when the pile is moving up, the dial gauge will show the displacement every time when you are, how much pressure you are applying. The alternate ways also, because instead of going for Kent ledge with self weight or dead weight, we can actually use this method by using the pile itself as a reaction frame. So, you do not need to stack up weights, only thing is the load is produced onto the test pile by means of the compression load, because you are just holding this Kent ledge frame on the sides using the piles. So, this is being a welded connection. So, always this anchor pile will be under tension. So, you need to have sufficient capacity of the anchor pile, so that means if you are testing a 3000 tons here, each one of them will have to be divided by 4 and sufficiently have designed with adequate penetration, because it is only tension. At least this pile have the end bearing, whereas the anchor pile will not have the end bearing. So, you need to have sufficient penetration. Sometimes it may become very large and basically or bigger than the test pile, because you need bigger capacity in tension than the test pile is being a compression capacity. So, you have to be little bit. So, that is where this method becomes a little bit difficult, because it might become very expensive, and when you compare with this, may be better, because you do not need to mobilize so much of material movement every time, because it is not one time. You will see that later on these sandbags have gone back and forth several times, because you got to do a loading sequence and unloading sequence, and you have to repeat the test at least 2 times, and that is where you find it is a time consuming process and also very expensive. Anchor pile seems to be very good, but then caution needs to be taken in terms of design. Make sure that when the pile is being tested, this the anchor that you have designed is not moving too much, otherwise you will be measuring actually a relative movement of the pile, anchor pile, and the pile being tested. Typical reaction pile setup. So, you can see here this is the pile being tested, pile requires to be tested, or otherwise you have the jack being placed at the, and these are the pile heads, the left side and right side you see the pile heads, which the piles already have been driven with a pile head, and when you just push this hydraulic jack upwards, the reaction being applied to the test pile, and the reaction piles on the left side and right side should have sufficient capacity, and basically that should be designed. And just a closer view of how the hydraulic jack is placed in the girder, so that it just reacts against the test pile as well as the reaction pile. Another load test using concrete blocks instead of sandbags. Many times people use this because it is easy to handle and can be used in multiple places, only require a storage, but in any case in construction sites you will find many of these concrete blocks spare capacities available there, but many times people use this sandbags because easy to dispose, because they can be used for construction work, no extra storage space is required, and each one of them will be weighed before placing it on the top, so that you know the weight what it is. Only the stability of them sometimes bit of a worry, because even a smaller eccentricity caused by either placement or by stability, the whole thing can be turned. In many places if you notice, pile load test failed because of the Kentledge tilted or Kentledge failed, which will cause quite a bit of problem. Whereas using concrete blocks is quite useful because it is very stable. Sometimes these concrete blocks will come with a shear keys, so you can have an opening at the bottom, and you can, when you place it, it will not go anywhere, and horizontal stability is well established. So, you can have a precast block specially for testing, not just for any other purpose. So, the ultimate load test is basically done to the load which is taken to the maximum failure capacity of the pile, which will be 2 times or 3 times depending on what the factor of safety used in the particular project or particular code of design, which is most of the time for IS codes we design for factor of safety of 3, which is for concrete piles, which actually says 2 to 3, but then mostly we use a factor of safety of 3. That means you find out what is the load that is designed for working conditions, take it to factor of safety of 3, and then find out. So, typically if you look at 300 tons is the working load, most of the 1 meter, 1.5 meter diameter piles, when you multiply by 3 you will take to nearly 1000 tons. So, imagine 1000 tons, what could be the requirement for dead weights. Working load test is typically 1.5 times the safe working load. So, we want to go for a slight overloading, but not to the ultimate stage, as long as you want to see passing off the working load and also have a little bit of margin. Again depends on how much design margin is available, and sometimes we reduce to 25%, which we normally call it overload test. Even mechanical devices nowadays, every one of them, the working load test is not acceptable. You have to go for slightly overload, because if the load exceeds the working load, even by a slight amount it should not fail. So, that is why overload test is about 25 to 50%. So, the two method of testing that we were discussing the other day is constant rate of penetration or maintained load. Constant rate of penetration is just, you can see here, 0.75 mm per minute. So, it is a quite slow process, and that is actually required by the British code. 8004 is for design of foundations. And maintained load test typically used in most part of this construction site in India. Is very easy to carry out. You don't need a sophisticated loop back system. You simply put the weight and get the, whereas the constant rate of penetration, you need a good amount of instrumentation to read the penetration backwards and adjust the pressure accordingly, and it can only be done by hydraulic system, not by this dead weight and the Kentledge methods. Is just not feasible. Whereas the maintained load test, even in a very simple method, which you need a dead weight and a jack, and the load shall be maintained constant until settlement rate is decreased to 0.25 mm per hour. So, what we normally do is you set up your Kentledge, put the weights, say for example 900 tons divided into say 5 steps or 6 steps. So, the step 1, put the load and just activate the hydraulic jack to transfer the load to the test pile, relieving the anchorage piles or support system, and then monitor the displacement. Initially the displacement of the pile may be larger, slowly reducing, indicating that the soil has achieved its failure state at that load, and then it will go constant or may slightly increase in a very low increment. So, once you see that it becomes a flat, the displacement graph is flat, that means you are not expecting any more immediate settlement. You may actually expect long term settlement, which may be several years, which is we are not interested in that. So, basically then how do you decide when to stop the or when to restart the unloading process, because every time you are going to unload it, bring to 0, then stack up to the next increment. So, first time say if you are having 200 tons and bring to 0, that means you have to take out the load and load it again to 400 tons. So, that process when you want to start, as soon as you see the displacement relationship is going flat, that will be better, but if the rate is still within this, then you can go. That means when the displacement is happening, you cannot do an unloading process. So, maintained load test is quite simple, we will see the procedure later on, something like this. So, you see here you put the 200 tons and then the displacement is increasing. So, what you will see is when you are doing an unloading process, if there is a elastic part, it will come back. If there is a permanent deformation of the soil, that will not come back, that will be residual. So, it will keep on stacking up. So, that is what we are interested in. Similarly, go to the second step. So, when the 200 ton weight is placed on the Kentledge, when you relieved the hydraulic jack, the load will go back to the support systems. Then you put another 200 tons on top of it, it will become 400 tons, take the hydraulic jack and load it onto the pile and just repeat the procedure until you reach the total test load. It could be ultimate test load or it could be working test load, and every time you do this you will see a loading unloading curve, you can see. So, basically you will be taking this as a displacement 9 mm or 8.5 mm for 200 tons. So, you can go and plot your load displacement in a different relationship, and typically will take several hours, because to get this flat curve sometimes you may have to wait longer time depending on type of soil. If it is a sandy material, you will get the displacement quickly, after that you will just become flat. If it is a clay, it might takes little bit longer time, but then instead of setting this criteria, IS codes actually give the time to wait for half an hour, wait for 1 hour, depending on type of soil, you may only vary little bit. So, if you look at the procedure given in IS codes, they give you the timing, every time step how much time you need to wait and then start the process of loading unloading. In fact, this particular procedure is taken from pile testing manual, which I was talking about on day 1. So, the design verification load, or it is basically the test load. If it is ultimate test, design verification load will be your total load multiplied by the factor of safety, or 25%, 50%, 75%. So, this procedure is just segmented into 4 subdivisions, 30 minutes. So, once you load 25% load, wait for 30 minutes, 30 minutes, 30 minutes, and the 100% load wait for a little longer time, and then during the unloading process only, because relieving of elastic compression will take just like this, it is not going to take time. So, unloading time they are just allowing you to only little time, 10 minutes, and then again restart the process 0, 100%, and you are going to do a overloading test. There you are going to wait for little longer time beyond the design verification load, if it is a working load test, and then repeat the procedure. So basically this is just a typical time versus increment of load. I have just taken from the manual of pilot load testing from the Association of Civil Engineering Contractors. Everywhere they use this, but if you look at IS codes, they may actually give you slightly different numbers and different timing, so depending on which jurisdiction you want to use. So if you look at this graph, load displacement curve for ultimate load tests up to failure. So you can see, depending on type of foundation material, you will see three types of. So if you look at the blue one, N bearing and weak rock, basically it increases and then suddenly fails. So you will see a certain capacity reaching, the rock is trying to fail. It's almost like elastic and then perfectly plastic. So something similar like this. And if you look at the black one, friction piles in soft clay or sand, you will see that a highly nonlinear, it keeps increasing, and then the failure rate will be slow down after achieving certain capacity. Or else if you have a friction pile in stiff clay, also will be very similar, but then there will be a downgrade effect because the stiff clay broke down when it is achieving the. So typically you will see something similar when you plot the when you extract the displacement from such plots. Nowadays you can automate this kind of things, so automatically you will get a time bound graph. Then you can later take the displacements, come up with the displacement versus the applied load graph, something like this, and basically you need to decide now what capacity is to be taken as ultimate or working load. So depending on what is the allowable or ultimate deflection that you want to permit. Remember when we were doing the TZ curve for clay and sand, we were talking about 0.1 inch for sand and then 1% for clay, something like this. So that corresponds to the ultimate failure. Whether you want to consider here for steel piles, it has to be decided by what is your the ultimate failure state you want to define. So once you define that limiting load or limiting displacement, then you can go on to the graph, you can take this is my ultimate failure load of the pile, beyond which we will not be able to take it. So that is the idea behind construction of this diagram, is just to make sure that your TZ graph you have made is going to be reflected here, and if you get a representative from here, and that will be realistic because this is based on test, whereas the other one is based on historical data and empirical methods. So you see here in this particular one, the ultimate capacity at 25 mm settlement is taken as 425 tons. So though it is highly nonlinear, some amount of plastic deformation has happened compared to when you go to the blue. If you look at it, this is completely elastic, and after that only becomes the plateau. So you can see the difference. So that's the way we want to determine when you do a testing. I want to determine what is the ultimate capacity. The thing is, you have to firm up what is the displacement at which you would like to take. For example, when you are designing a structure, you will always have a limiting deflection in both horizontal and vertical working load conditions. So then if you are allowable capacity you want to find from this, then suppose you are fixed at 10 mm is the allowable displacement during service life of the structure, then 10, you just go to 10 mm, the pile has achieved say 350 tons. Now if you take the ultimate capacity, apply a factor of safety of 3 or 2, you will only get something like 120 tons. So that is what will be revealed here. If you do not know how this graph is going, what you are trying to do is, if you take 420 tons, join from here straight away to 0, make a straight line. That is what you are doing by means of factor of safety, 420 divided by factor of safety of 3 on load. Whereas if you have this graph, you know very well that you can allow maximum of 10 mm during its service life with the factored load or unfactored load. Then you can decide how much margin you have. Almost a large margin is available. When you take 10 mm and restrict to 10 mm is the displacement, 420 divided by factor of safety of 3 you will get around 130 tons, that is what you are going to permit. But actually the pile has got reserve capacity up to 350 tons at the same 10 mm displacement. So that will be the difference when you have a non-linear load deflection curve, especially after testing. So this will give you a picture how much extra margin you have because of the soil behavior. And if you take this one, you won't get anything better, isn't it, because you are having almost a linear relationship. If you take that, will be the capacity of say 550 tons divided by straightaway factor of safety of 3, you will get somewhere around 180 tons. Whether it is 10 mm or 5 mm, you are going to just linearly prorate, so does not matter. So that is the idea of constructing or establishing load displacement characteristics up to failure. If you have only established up to, for example, some lower displacement, because you are not going to do a failure test, you are going to do a working load test just up to the linear portion, then you may not actually reveal how the behavior after this. This is why at least 1 or 2 piles at the site you have to do up to failure to see how much margin you have. It can behave this way, which we do not know unless you do the testing. Then we also move on to horizontal load test. Basically similarly you can do a horizontal load test. One of the biggest problem is doing reaction. See, just now we have learned about vertical load test with supports arrangement, somehow we can make it because it is a similar piles can be driven. But when you do a horizontal load test, you need to have firm ground or firm support condition just to measure the horizontal displacement of the pile, and also to transfer the reaction from the jacks, which is going to be a big challenge. So doing in onshore itself is a challenge, then when you are doing it in coastal or offshore conditions, it is even challenge because you have to design a system stronger than the test pile itself and install it. And also you can carry out cyclic load test in cases of coastal structures where cyclic behavior is required for degradation effects. So typically you see here some working platform is required. I have just straight away gone to the coastal areas where some of the berthing structures we still do this lateral load test to establish the capacity in horizontal direction. So, but most of the structures on land normally we do not do a horizontal load test, not really required because predominantly it is not so much problem so far for buildings and bridges, predominantly gravity load. So you see here we have a test pile which is in yellow color, and we have a reaction pile and just the jack. Now you see here the jack is placed in between, attached to both the pile heads, and the jack is trying to expand by giving horizontal load to the test pile. The reaction is transferred to the reaction pile. Now if the reaction pile is stable, the reaction pile displacement is smaller or ignorable, then what you are measuring is the pile head displacement. Otherwise you will be measuring the relative displacement of, because this pile is also moving, this other pile is also moving, then how much we have to find out. So you need a calibrated system to find out what will be the displacement, which will be quite tough because you can theoretically calculate, but then it may not be correct. The reference will be used, another few numbers of piles is required, or support system is required to support all this, as well access to these places. So you will see that horizontal load test becomes reasonably expensive because you have reaction frame and you also have a reference frame. This is a reference frame, the green color what you see is a reference frame against which you will do the measurement of the displacements, and they need to be placed sufficiently wider spacing. Otherwise what happens when you are doing reaction here, when the pile is trying to bend, it puts undue pressure on the soil, and that soil gets affected by this particular location, and the behavior of the lateral capacity is going to be affected to some extent, and that is why we have to have minimum of 3 diameter or 4 diameter or 5 diameter. Once you become wider spacing, mounting of jacks become a problem. You need to design a frame, and that is going to put you into a support system. Together it has to be mounted onto the 2 piles, which needs to be free to move. So that is one of the challenge. A typical cyclic load test results or plot how you carry out loading and unloading process. Basically the horizontal load versus lateral displacement. You take it to one cycle at particular load level, bring it to 0, repeat it few times just to get the repeatability, and then again increase to a higher load, repeat it again, load and unload. Since there is no dead weights are involved, here is only a hydraulic jack, doing such load test is very easy. Then you repeat it again and again for various loads and stop when you actually reach the expected displacement. For example, ultimate load test you are trying to do for 100 mm maximum. If you are doing a ultimate horizontal failure load test, then you can go up to failure of the pile and stop. Otherwise you have a predetermined load by which it will not be a larger capacity. Most of the pile, if you look at 50 tons or maybe maximum 70 80 tons, unlike the vertical capacity where you have thousands of tons or sometimes very large number. Here it all be restricted by the pile horizontal shear, because if the soil does not fail, what will happen? The pile will fail. So if you look at the shear capacity of the pile, that will give you the maximum magnitude by which you can test. In fact, you will apply a factor of safety on it. What you do not want, you do not want the system to fail before the soil fails. System means the pile itself or the anchor pile itself. So you will find out what is the bending capacity of the pile, of structural capacity and shear capacity. Make sure that you have got sufficient factor of safety available on the structural system prior to go to ultimate load test, because you do not want the system to fail, but then it will be a catastrophe. In some cases, in the coastal structures like berthing structures, we may require pull out test, because some of the piles are actually going to have a tension capacity requirement, especially when you build a berthing structure. The front pile will be in tension, the back pile will be in compression when you are having ships are berthing against the berthing structure. So such you may require a pull out test instead of a compression test. It is exactly opposite of it, only the Kent ledge placement and the hydraulic jack placement is in a reverse condition. If you just go back to our this test somewhere here, I think something like this. So this one is anchor pile method, you are doing a compression test, just reverse the process and placement of the hydraulic jacks, you will get the. So basically the Kent ledge arrangement is attached to the reaction pile, and there will be stress blocks and you have the hydraulic jacks, and then you attach your brackets welded to the test pile itself. So what you are trying to do is you are compressing the reaction pile and pulling up the test pile. So basically you are just reversing the reaction just to get what tension capacity is available. Many times you will require this for coastal structures, but magnitude will be not very big, few hundred tons. So what are the things that we need to note down when you are doing a compression load test? The support frame needs to be designed appropriately, because you have such a large weight to be placed. Support piles needs to be placed away by 3 diameter, that makes the, so if you have a 2 meter diameter pile, you need to go for either side 3 meters, 3 times 2 meters, 6 meters. So the frame becomes almost 12 by 12 or 15 by 15. Structural capacities of test pile as well as the support piles needs to be made sure that it has got adequate capacity. Special care must be given to the test pile, because it is a cantilever, whereas actually the same pile when it is working in the actual structural system, it may not be a cantilever, it may be a combined pile heads with other structures, whereas when you are doing testing it is a pure cantilever. You must remember what is the difference between the pile in a temporary condition, which is a cantilever, to a supported pile in the permanent condition. Because of Euler buckling, the load capacity will come down drastically. So you cannot think about always you have a pile 1 meter diameter in a permanent system which is connected to a bigger structure which may not behave as a pure cantilever. So your effective length and the fixity conditions are different. Your 1 meter diameter pile may work there, whereas the same 1 meter diameter pile when you bring to the test category, it becomes a pure cantilever. Number 1, Euler buckling load will be definitely half or less than the actual buckling capacity. So, when you are doing the same ultimate load test here, you do not want the pile to fail. So, what we really need to do is keep the diameter same, because you do not want to change the pile soil interface, is not it, because we want to test the 1 meter diameter. But what you can do is you can increase the wall thickness to increase the bending stiffness, buckling capacity, shear capacity in such a way that structure does not fail, but the soil pile interface is being tested. You understand the idea, no? So, you need to make sure this, otherwise you bring the same pile and do the testing, before the soil fails the pile collapses and then it puts the whole system into problem. So, that is what you have to make sure. So, what highest codes are suggesting, instead of what we saw was 25, 50, 75, they have divided into 5 sub segments of loading, 20, 40 and 60, 80 to 100. So, that is just a little difference, and basically loading unloading cycles almost similar. I am not very sure whether I have copied the time cycle. You can look at the code, the times also given 30 minutes up to 6 hours. So, you can refer to the code, but what the criteria I wanted to look at it is basically when do we decide it has achieved its ultimate capacity, and it is applicable only for concrete piles. You cannot apply this one to steel tubular piles, it is not under that particular code. So, if you look at this graph, I have just plotted one of the recent last year test. 2/3 of final load at which the total displacement attains a value of 12 mm. So, you just look at the graph and just go around, apply the criteria number 1, the safe load on a single pile for an initial test should be least of the following. So, the criteria is given, do the testing, come back here, plot the graph and look at these criteria, whichever is lower, that is your safe working load. So, that is the criteria that you are going to apply, and of course, this is written on the basis of onshore structures. 2911 is a code for bored concrete piles for onshore applications, not even for coastal applications. That is why you cannot blindly apply this principle to a coastal structure or to an offshore structure, where displacement criteria are different from the onshore structures. You will see that they are very strict in terms of displacement, because these are applicable to buildings and bridges, or to some extent industrial structures on land where they are controlled by deflection. Whereas, if you go to coastal structures and offshore structures, the displacements are definitely going to be larger. You can't even think of the criteria here, because here they are talking about 25 mm. When you think about a coastal or offshore structure, you are going to have several 100 millimeters of displacement because of the magnitude of the horizontal loads. So, you have to be little bit cautious and apply the principle differently. 50% of final load at which the total displacement equal to 10% of the pile diameter. So, these are the 2 criteria. So, if you see there the criteria 1 and criteria 2, you can find out whichever is giving you the capacity. I think even the lateral load also similar criteria is given. 50% of the final load at which the total displacement increases to 12 mm, final load at which the total displacement corresponds to 5 mm, and then any load correspond to any specified displacement. So, this is at least some option is given for horizontal load. So, according to your project specific requirement, so you specify I can go up to 50 mm, then I can look at. So, that is the thing, that we need to have a decision making process. Just doing load test alone will not be good enough, you do not know what to do with that. So, what you need is the demarcation, what will be an acceptable displacement for that particular type of structure, and the applicable code in force. What the API says, we do not have a procedure to restrict the displacements. Unfortunately, there is no requirement, because we do not need, because offshore structures are subjected to so much higher loading that if you restrict 25 mm displacement, for example, your structure will be so much bigger and may not be practical. So, that is why the adapted method by API is to design by the factor of safety, which gives you an adequate safety against pile failure or premature failure, and at the same time you have a ductile material which is steel, and you are not worried about failure by other means of fracture, because the worry in concrete structure is larger displacement either in vertical direction or in horizontal direction. can cause superstructure failure by fracture, because the concrete cannot fail by ductile. So, that is one of the reason why most of these concrete codes they restrict the displacement to smaller, whereas the offshore structures we never build using except the concrete gravity platforms. All the fixed type of structures are built by steel material, has higher tensile capacity and also have a ductile characteristics. So, in that reason we go by the method of engineering based design based on soil properties with adequate factor of safety, and we leave it there. We do not want to apply the restricting displacement. The reason why we develop PY, TZ all that is to make sure that pile is actually subjected to the actual load displacement behavior and the bending stresses are calculated. So, if you have a larger displacement, what happens is the pile is subjected to larger bending, and larger bending means the requirement of section and the diameter and the thicknesses are going to increase. So, you design for it rather than trying to limit the displacement of the pile to lower value and increase the larger diameter. So, that is exactly the design method adapted by API. So far I do not think any problem with that idea. One of the other issue with the concrete pile supporting concrete structure is the architectural finishes and serviceability requirement. That is why we restrict the displacements to very small value. In fact, the reason why we restrict to 1 inch is because of that. You know, if you have the structural system capable of taking, but the architectural finishes and service functions will be seriously disturbed. That is why buildings are designed for smaller displacement